Sixth grade, Module 6, Lesson 16, Classwork, Understanding Box Plots. Exercise 1, Supreme Court Chief Justices. Number 1. The Supreme Court is the highest court of law in the United States, and it makes decisions that affect the whole country. The Chief Justice is appointed to the court and is a justice the rest of his life unless he resigns or becomes ill. Some people think that this means that the Chief Justice serves for a very long time. The first Chief Justice was appointed in 1789. The table shows the years in office for each of the Chief Justices of the Supreme Court as of 2013. So here are all the Chief Justices that we've had since up until 2013. So their names, how many years they served, and what year they were appointed. It says, use the table to answer the following. Which Chief Justice served the longest term and which served the shortest term? How many years did each of these Chief Justices served? So let's start with the shortest and longest. So the shortest term was here, John Rutledge. He served 1 year. So John, he did not last long. And the longest, let's see, who has the most years? This person has 28 years, but John Marshall here has 34 years. So he wins for longest. John Marshall. Served for 34 years. So that's basically our minimum and our maximum if we were to make a box plot, dot plot. B, what is the median number of years these Chief Justices have served on the Supreme Court? Explain how you found the median and what it means in terms of the data. So median number of years, what we are going to do is list them in order from least to greatest. So what are you going to do? I'm going to list in order from least to greatest, and then I will come back after I do that. Okay, I have them all listed out here in order from least to greatest, so let's find the median. There are 17 numbers, so you can either go through, cross off, find the middle, or if we split 17 in half, we're going to have 8 on one side, a middle number, so that middle number, and then 8 more numbers, and this middle number will be the median. All those 8 plus 1 plus 8, those add up to 17. So I'm going to count over 8. 1, 2, 3, 4, 5, 6, 7, 8. So here's our median, 11. So our median is 11. You could have also found that by just crossing off on either side and getting to the middle. So we listed in order from least to greatest. And then what does that mean when we find the median? Median is 11. That means that approximately half of the justices served less than or equal to 11 years, and the other half served greater than or equal to 11 years. Okay, C says, make a box plot of the years the justices served. Describe the shape of the distribution and how the median and IQR relate to the box plot. Okay, so we need to make a box plot with this data. So we're going to have the information we need to know is the minimum, the maximum, the median, which we already know is 11, quartile 1, and quartile 3. So the minimum was 1, the max was 34, so let's find quartile 1 and 3. So the middle number we can just cross off, there's 8, so we can split them in 4. Between 6 and 7 would be 6.5. So the bottom half quartile is 6.5. The top half, we split it 4 and 4. In the middle would be 18. So let's make our box plot. So let's say number of years served. Or I'm just going to call it justices. Okay, our minimum was 1 and our max was 34. So let's go from 0 to 35. I'll count by 5s. Okay, so our median is 11. Our quartile 3 was 18. And quartile 1 was 6.5. So over here, let's make a rectangle. And our max is 34. So up there, and our minimum is 1. Describe the shape of the distribution and how the median and IQR relate to the box plot. So the IQR is going to be the range from here to here. So the IQR is 6.5 to 18 years. So if we subtract those, we get 11.5. So about half of the Chief Justices had terms in that 11.5-year interval. So that's where about half of the justices lie in there. Describe the shape of the distribution. So we could just say that they seem to have more justices serving on the smaller end than the larger end. If I see here where it's distributed, it's more heavily leaning towards this way because the box is more down here on this end rather than up here. So let's just kind of describe all of that. So let's say the distribution leans towards the left, so most justices served on the lower end for a fewer number of years. The range is 33 years. Right, the minimum was 1, the maximum was 34, so the range is 33 years. The IQR, which was 18 minus 6.5 is equal to 11.5. So about half of the justices had terms in that 11.5-year interval from 6 years or 6.5 years to 18 years. And D, is the median halfway between the least and the most number of years served? Why or why not? So is this median right here halfway between 1 year and 34 years? Well, it's pretty obviously that it's not. It's actually closer to the minimum, the 1 year, because kind of what we talked about, this data is leaning more towards the left side or the lower end, where most of the Chief Justices served on the lower end of that year served. So let's say no, it's not in the middle. The data are clustered in the lower end of the distribution. And you could go on to explain a little bit more, but we kind of talked about that in C. Exercises 2 and 3, downloading songs. Number 2, a broadband company timed how long it took to download 232 4-minute songs on a dial-up connection. The dot plot below shows their results. What can you observe about the downloaded times from the dot plot? So on the dot plot, I noticed that the minimum time was a little bit above 4 minutes, and the maximum time was a little bit greater than 17 minutes. And I think about most of the data lies kind of here between 8 and 13 minutes. That's where a lot of the data is gathered. So you can have other observations too. That's just what I'm going to say. So I'll say the smallest time was less than 5 minutes. And the greatest was more than 17 minutes. Most of the data falls between 8 and 13 minutes. B, is it easy to tell whether or not 12.5 minutes is in the top quarter of the downloaded times? So 12.5 minutes is about right here. Is it easy to tell if that's within that top quarter, or the fourth quartile there? I mean, I can't tell. We would have to have a box plot to tell that and find all the quartile information. So no, we can't tell. No, we can't easily tell. C, the box plot of the data is shown below. Okay, so now they've given us the box plot. Now answer parts A and B above using the box plot. So what was A? What can you observe about the downloaded times? So what do we notice? I noticed that the median is about 10.5. We can still see the minimum and the maximum, so that's not anything new. We can see that quartile 1 is here at about 8.5, and quartile 3 is a little over 12, so maybe like 12.5 or 12. Let's just go with 12. So let's answer A. I'll say that, let's say about half the times are above here. Maybe that's like 10.5 or 10.6 minutes. And we could say about half the times are between 8.5 minutes and 12 minutes here. So that's what the IQR range is. Okay, so B was asking, is it easy to tell whether or not 12.5 minutes is in the top quarter? So now it is going to be easy. So it's 12.5 minutes. 12 and a half would be like right there. So yes, it is in this top quartile. So yes, 12 and a half minutes is in the top quarter. Right? It's above quartile 3 right here, so it's in the top quarter. D, what are the advantages of using a box plot to summarize a large data set? What are the disadvantages? Okay, so let's start with advantages. We'll just kind of make a little list. So with lots of data, so we're talking about a box plot. So what are the advantages of using the box plot? We can see general patterns. We can easily see the median. What else? We can shows the 5-number summary. Right, your min, your max, your median, your quartile ranges. So what are some disadvantages? I would say the main disadvantage is you don't get a real sense of the data. So like this box plot, it shows us, a summary of the data, but we don't get to see every individual data point like we do on this dot plot. So I would say that's the main disadvantage, is that it does not give specific values. Not give all the individual values. All right, number 3, Molly presented the box plots below to argue that using a dial-up connection would be better than using a broadband connection. She argued that the dial-up connection seems to have less variability around the median, even though the overall range seems to be about the same for the download times using the broadband. What would you say? Okay, so these are the 2 graphs that she has shown, but what I notice, first off, is that this is in minutes and this is in seconds. So we're using different scales. So this is like 4 minutes and this is 1.5 seconds, up to 7.5 seconds. So everything over here is a lot quicker than over here, even though it looks like it's further down the scale. So it's very important that you notice what we are measuring here, because we could have easily been fooled by just looking at these box plots and not noticing. So let's say that the scales are different, so that they're hard to compare. So you can't just look at the box plot. The time to download via broadband is only, or the median time is only about, 5 seconds? Whereas using dial-up takes about, on average there, the median, about 10.5 minutes. So big difference. Would you rather wait a couple seconds or 10.5 minutes? So make sure, the main point of this is to make sure that you're noticing the scales here, and that they are very different. Exercises 4 through 5, rainfall. Data on the average rainfall for each of the 12 months of the year were used to construct the two dot plots below. We have St. Louis and San Francisco. This is the average monthly precipitation in inches. How many data points are in each dot plot? What does each data point represent? So let's start with St. Louis. St. Louis and San Francisco. Let's count up St. Louis. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Which, now that I reread it, there should be 12 because we're talking 12 months, right? 12 months of the year. So what does each dot point represent? Each one would represent a different month. So each represents a different month of precipitation in inches. B, make a conjecture about which city has the most variability in the average monthly amount of precipitation and how this would be reflected in the IQRs for the data from both cities. So which one has the most variability and which one has the most? I'm going to say, just by looking at them, St. Louis, they're all kind of gathered up here, whereas San Francisco are much more spread out. So I would say that San Francisco is going to have a lot more variability and in return also a much larger IQR. So San Francisco has the most variability. And will have a larger IQR than St. Louis. C, based on the dot plots, what are the approximate values of the interquartile ranges for the average monthly precipitations for each city? Use the IQR to compare the cities. So in order to find this information, we need to list them in order from least to greatest, find the medians, and then we can go from there. So I'm going to stop and list them in order, both in order from least to greatest. All right, I've listed them out from the data in order of least to greatest. So let's go ahead and find the minimum, maximum, median, quartile 1 and quartile 3. So the minimum, well, let's do St. Louis first. The minimum is 2.5 and the maximum was 4.9. So let's find the median. So since there are 12, I'm going to count up 6 and find the middle. So there's 1, 2, 3, 4, 5, 6. So the median's right there in the middle. But they're both 3 and 4/10, so 3 and 4/10. Now let's find the median in between those. So we have quartile, the bottom half and the upper half. Let's find the median of those. So let's start with the lower half. I'm going to find in the middle there, between 3 and 3.4 would be 3 and 2/10. And then the middle here, they're both just 4 and 2/10. So the IQR would be 4 and 2/10, Q3 minus 3 and 2/10, which is 1. So the interquartile range there is 1. And then let's do San Francisco. We'll have the minimum, maximum, median, quartile 1 and quartile 3. So median, if we count up 1, 2, 3, 4, 5, 6, it's in the middle of 1 and 1/10 and 1 and 5/10. That will be 1 and 3/10. Find the median of those. So let's do the lower half. Right here in the middle, So we're splitting 2/10 and 2/10, which would just be 2/10. All right, the minimum was 0, max is 4.6. And then up here, in the middle of 3 3/10 and 4 5/10 would be 3 9/10. So these are all in inches. So then our IQR would be equal to 3 9/10 minus 2/10. So we do quartile 3 minus quartile 1. So there, the variability is 3 7/10. So that is for San Francisco's IQR is 3 7/10, whereas St. Louis's IQR is 1. So we were right. St. Louis does have a much larger variability. So let's say, let's just explain what we did. So St. Louis IQR is 1, and San Francisco IQR is 3 7/10. So about half the monthly, so about half of the middle half. Let's reword that a little bit. About the middle half, because remember we're talking about the middle part, about the middle half of the monthly precipitation amounts in St. Louis are within 1 inch of each other. And then we can just say in San Francisco, they are within about 4 inches of each other. So lots greater variability. D. In an earlier lesson, the average monthly temperatures were rounded to the nearest degree Fahrenheit. Would it make sense to round the amount of precipitation to the nearest inch? Why or why not? I would say it wouldn't really make sense to do that, because when we're talking about numbers so small as 1, like a few tenths can really matter. Like the difference between 1 3/10 and 1 9/10 varies greatly. And if we're just kind of rounding both of those off, it makes a big difference. So I would say no, because the numbers are pretty close together. But you can have a different opinion of me. No, because the numbers are already really small. Five, use the data from exercise 4 to answer the following. Make a box plot of the monthly precipitation amounts for each city using the same scale. Okay, they've already done it for us, and we already have the numbers, so this is going to be easy. All right, so let's start with St. Louis. We had, let's see, here was our St. Louis info. So median is 3 4/10. Let's start there. So median was 3 4/10. Right about there. What was quartile 1? 3 2/10 and 4 2/10. So we have 3 2/10 and 4 2/10. Draw our box. And then what were the minimum and maximums? 2.5 and 4 9/10. I'm going to draw out to 2.5 and up to 4 9/10. Let's do San Francisco. Minimum was 0, max was 4 6/10. So median was 1 3/10. Quartile 1 was 2/10, and quartile 3 was 3 9/10. We've got down here at 2/10, and then up here at 3 9/10. That is a very large rectangle. And then our minimum was 0, and our max was 4 9/10, all the way up there. So those are the different box plots. B, compare the percent of months that have above 2 inches of precipitation for the two cities. Explain your thinking. So above 2 inches for both cities. Where's 2 inches? Okay, well, St. Louis doesn't have any. Whereas San Francisco, I can't tell how many we have, but more than half, because here's the median. So more than half of St. Louis or San Francisco have less than 2 inches, but all of the months in St. Louis have greater than 2 inches of precipitation. So let's say in St. Louis, the precipitation is always greater than 2 inches, whereas in San Francisco, more than half of the months are less than 2 inches. So very big difference there. How does the top 25% of the average monthly precipitations compare for the two cities? So the top 25%, that would be for St. Louis, it's above 4 inches. And for San Francisco, it's pretty close to 4 inches. So I would say that they're pretty similar in their top 25%. Let's just say the top 25% of both cities are similar, are very similar. They are spread over the same interval. D, describe the intervals that contain the smallest 25% of the average monthly precipitation amounts for each city. So now we're looking at the smallest 25%. So we've got here, St. Louis ranges from about 2.5 to 3 inches, whereas San Francisco is like 0 to 0.2 inches. So this is where they vary greatly. They're very, very different. Let's say in St. Louis, the bottom 25% are between 2.5 and 3 inches. In San Francisco, the smallest averages are much lower, ranging from 0 to 0 and 2/10 inches. And E, think about the dot plots and the box plots. Which representation do you think helps you the most in understanding how the data vary? I personally just like looking at dot plots better. Maybe you like box plots. This is kind of a question about you. I like dot plots because we can see the individual values, personally. But you write what you like. Maybe you like the values that the box plots provide. It's up to you. Because I can see the individual values. Okay, and then that is the end. This is just a graph, a chart that shows the exact times. So up here in the chart, it was just kind of rounded. These show the exact times if you're interested in that data.